Your screen is, sir, visible to us, sir. Just you have to make full screen and.
Yeah. So is it visible now? I hope so.
Yes, sir. Yes, sir. Yes, sir. It is visible
Okay.
now.
Okay. So very good afternoon to all the participants, respected faculty members, delegates of this short-term training program. And thank you, Dr. Goda, for this introduction. As a faculty, it's all our part of duty to do some research work, guide some PhDs, do some project work, establish new labs, new techniques, learn new techniques, both in terms of computational and experimental aspects. So for next 40 minutes or so, if I'm correct, that much amount of time would be available to me, 35-40 minutes. I would be talking about heat transport investigation of some complex nanofluids. Those who belongs to basic science engineering background or technology background can understand the aspects of heat transport and complex fluids. So the heat transport indicates that transportation of heat from one system to another system, or from one component of a system to another component of a system, and it has its inherent utilization, application, and immense applications are there, both in terms of man-made materials and natural circumstances. It involves day-to-day human behavior as well as industrial applications and industrial processes. As far as complex fluids are concerned, there is a class of fluid which follows Newton's law of viscosity, which says that stress should be directly proportional to strain. If that is being followed, the fluid is said to be Newtonian fluid. Else, if that condition of the Newton's law of viscosity is not being followed in word and spirit, there is another class of fluid that comes into the picture, and we call it non-Newtonian fluids, sometimes also known as complex fluids. And therefore, the complex fluid has its own complexity in terms of the flow behavior. And these are very common, though we call it complex fluids. They are very, very, very common in our life, as common as the samosa and the ketchup that comes with that samosa. So I hope you remember that when you were having this delicious samosa or pakodi in canteen or at your home or hostels, wherever you are, the sauce in the bottle, you need to pour it on plate. Then what happens that it do not comes down on its own. You have to apply a little bit of stress. You have to apply a little bit of force. You have to shake that bottle a little bit in order to initiate the flow of that ketchup, sauce, jelly. That happens with most of the these kind of fluid products, and therefore they do not behave. This tendency comes because they do not behave in a Newtonian fashion. They show some kind of complex behavior, and that's why they are called non-Newtonian fluids or complex fluids. We here deal with nanofluids, where nanofluid is a class of fluid where a base fluid is mixed with certain nanoparticles in them. Once they are mixed with some nanoparticles in them, this the behavior no more remains what you call Newtonian, rather than it becomes non-Newtonian. And this colloidal solution of the nanoparticles, though very small in quantity, sometimes as low as 0.05%. 0.05%. What does that mean? That means 0.05 part in 100 units, or 0.05 gram in 100 grams. If I talk in terms of mass, that means 0.5 gram in 1 liter of fluid. Just 0.5 gram of nanofluid, nanoparticles in a fluid makes that fluid a nanofluid. And the flow behavior of that nanofluid, it becomes complex. Some participants are having their microphones switched on, please. Please switch off your microphone. That would be easier for clear dissemination of the communication from my side. So these nanofluids behave slightly different than the conventional Newtonian fluid, and that's why we call them non-Newtonian fluid. And these kind of nanofluids, they undergo heat transport phenomena very significantly. No, let us first understand where these nanofluids we can found in our daily life. So the colloidal solution of the tropical medicines that we use is on the skin. There could be a suspension of nanoparticles and medicine in nano form, and some base material. Those base materials primarily consist of water, and sometimes carbopol powders are mixed into them in a very, very, very small quantity to make them stick to the surface in order to enhance its viscosity, in order to enhance its stickability on the surface, because the topical medicine we want to stick on the surface. Same applies to the beauty products, the certain products that are used for cosmetic applications. You know, these cosmetic applications products, pharmaceutical products, they contain sometimes very small amount of nanomaterials. So does addition of this nanomaterial make them any different from this bare material? The answer is yes. First, their flow behavior pattern changes. They do not show the typical Newtonian behavior, rather than they show some non-Newtonian behavior. One of them is a very common, that is the yield stress behavior. And once I talk about yield stress, they can be classified as yield stress nanofluid. Okay, so let us try to understand this how this nanofluid, yield stress nanofluid, once they are subjected to some kind of heating or cooling, how they do behave. Okay, and some mesoscopic study of this behavior we will try to understand. If time permits, then the thermorheological characterization of water based nanofluid we will take into consideration. Okay, so the motivation is some fluids such as electrorheological, magnetorheological fluids, you know, which are utilized in braking systems, clutches, dampers, in order to enhance its shock absorbing capacity. They act as these kind of fluids. Drilling fluids, drilling coolants, lubricants, along with transporting agents of drilling cutting systems, they also behave in a similar fashion. And as you go deep inside the well, drilling wells, what happens is the temperature at the bottom hole gets higher and higher because of continuous drilling, because of continuous friction contact between the moving mechanical parts and the fluid kept over there. Okay, and many a times rapid cooling of these systems are desirable. Okay, and mixing of external particles, maybe nano or micro, in these fluid can be a way of enhancing the cooling, because these nanoparticles being solid, they have significantly higher thermal conductivity. Okay, and therefore these fluids could be of great use. And by and large, we try to model them as a yield stress fluid by using the Bingham rheology. If you go to the available literature survey and look into the available literature. Then Turan and his team at different places, primarily at Liverpool University, and then one university in Turkey Technical University. There is a big group. Uh, uh, they have very, in a massive way, in a very aggressive way, they have investigated two-dimensional investigation of laminar natural convection by using Bingham plastic in a situation where they are enclosed in a cavity and with differentially heated side walls. A lot of work has been done by this group. Couple of students under me has also carried out computational as well as experimental investigation on locally heated Bingham fluid when they are heated from the bottom locally. Okay, experimental and numerical investigation of Rayleigh-Bénard convection has been carried out by some of the investigators. Okay, and therefore we can say that this Rayleigh-Bénard convection, where a classical problem of Rayleigh-Bénard convection, where the bottom is the heated surface and the top is the cooling, and in between the fluid is trapped, has been reported in major of the cases. Without going into much detail of them, let us come to the problem. As I told you that I would be taking couple of problems, and with the help of those couple of problems, I'll showcase the importance of both nanofluid, the behavior of what happens when they are subjected to temperature gradient, heating or cooling, and how does the thermofluid behavior of nanofluid comes into the picture. Now, so primarily, this is a case where we had a square enclosure, an enclosure of a square cross-section, and it is filled with typical yield stress nanofluid, and it is differentially heated. Okay. The rheology of the Bingham fluid is modeled, this rheology of this nanofluid is modeled by Bingham model, where tau is represented as tau y plus k gamma dot, where tau is the stress, tau y is the yield stress. Yield stress is a kind of stress which is required to cause a Bingham fluid to flow. Like you remember this ketchup, it do not comes down on your own. You know, if you had an opening and you had as a what you call you had Pepsi can available to you, get an opening at the top, flip it, the fluid in the can will start flowing down because of the gravity itself. It is sufficient enough. But that do not happens with the toothpaste. You take the toothpaste tube, remove its cap, flip it down. Will the toothpaste will come down on its own? The answer is no. Same thing happens when you try to do, with jam or jelly or the sauce, tomato sauce in the canteen. You have to shake it a bit before it comes down. You have to squeeze the toothpaste tube before the material starts flowing down, come out of the opening. Why does this happen? Because the material shows some resistance. Material, fluid. I'm not using the word liquid. I'm using the word fluid. The fluid shows some resistance to flow, resistance to deformation, and a prior threshold external force or stress need to be applied before these materials starts flowing, and henceforth these they show some in threshold resistance, and these resistance are termed as yield stress. So applied stress should be slightly higher than the threshold yield stress in order to cause this fluid to flow, and that's why they are termed as yield stress fluid. So usually this tau should has been equal to mu gamma dot, where tau is the stress, gamma dot is the strain rate, and mu is the ratio of the stress to strain rate, that is termed viscosity. But in case of Bingham fluid, this stress is not directly proportional to mu gamma dot, rather than it is equal to tau y plus k mu gamma dot. So this tau y term additionally comes into the picture, and that plays an important role. Yeah, this constitutive equation of the Bingham model has been shown here, where tau, if it is greater than the yield stress, then it is equal to tau y plus mu gamma dot. Else, there would be no deformation. If the applied stress is less than the threshold stress termed as yield stress, there would be no deformation. And the case of no deformation, you apply the stress, it won't deform. The same thing happens with the dough, gunda hua atta, or the clay. They also behave in the similar fashion. There are good number of examples for fluids following this Bingham model. And the problem that we have taken into consideration is the convective heat transport in yield stress fluid confined in a computational domain of square geometry, where the bottom part you can see is the heated one. Yeah, you can have a look here. This TH represents a slightly enhanced temperature. You can call it high temperature. So bottom part is the heated one. The enclosure is filled with nanofluid, which we assume as a yield stress one. The top part is the cooling one. Okay, whereas the rest of the two vertical walls are neither moving nor they are conducting. They are insulated one. So all the four walls are stationary. The bottom is the thermally active. Bottom and top is thermally active.
Recording in progress.
Bottom and top is thermally active, and the vertical side, left and right hand side walls are neither thermally active, not moving. Okay, so we will start with the governing equation in non-dimensional form. Those who had taken a course in fluid mechanics or heat transport or heat transfer, heat and mass transfer, convective heat transfer, they all must be aware of this set of governing equations and the process of non-dimensionalization of the parameters. For example, the spatial coordinate of x and y has been non-dimensionalized by as x by L, dimensional y by L, velocity as dimensional u, velocity by characteristic velocity v star, that has been defined as g beta delta t L root over. Similarly, capital V is small v by v star. The temperatures are dimensionalized by using term something like T minus Tc by Th minus Tc, that we are representing theta. So theta is the dimensionless temperature, and the dimensionless pressure has been represented as dimensional pressure by rho v square, where rho is the fluid density and v star is the characteristic velocity. If that's clear, then we can come to the governing equations. The first and foremost is the steady state continuity equation that tells us del u by del x plus del v by del y is equal to 0. That's the law of conservation. It comes from the conservation of mass. It's also known as continuity equation. Followed by, because it's a two-dimensional problem, it's a two-dimensional geometry that we are trying to crack down, assuming that the third dimension is significantly large, so it won't make any difference to the problem. Henceforth, considering it as a two-dimensional problem, the x direction momentum equation and the y dimensional momentum equation has been mentioned just below this continuity equation. So x direction momentum equation, I'll explain a bit. U del u upon del x plus v del u upon del y is equal to rho by rho nf, whereas rho f is the density of the base fluid and rho nf is the density of the nanofluid. So the density of the nanofluid is expected to be slightly higher than the density of the base fluid multiplied by minus del P by del X pressure gradient plus 1 by root over GR, where GR is the Grashof number representing the ratio of the buoyancy forces, okay, because of the temperature gradient to the rho square G beta delta T L cube upon mu square, that is viscous forces. So buoyancy forces by the viscous forces is represented by the Grashof number, and then you have a shear stress term del tau xy by del x plus del tau yy plus del y plus beta nf by beta f if there is any body force term that comes into the picture. Same has been taken into account in both U and V direction. In V direction, you had additional term BNF by beta F. That is because of the presence of the acceleration due to gravity in the Y direction. This additional term of B has been coming into the picture, and it is being closed. The governing set of governing equation is being closed by the energy equation, where the U del theta by del X plus V del theta by del Y, the convective term, is equal to alpha NF by alpha F. Alpha is thermal transport characteristics, okay, K by rho C, okay, multiplied by 1 by PR. PR stands for Prandtl number, multiplied by GR, del square theta by del X square plus del square theta by del Y square. In this fashion, this governing equations consisting of momentum, continuity, and energy equations are represented here. This constitutive equation of the Bingham model is having a complexity because of the inherent discontinuity at tau is equal to tau y. Okay, because these equations very clearly states that the deformation would be there only if tau is greater than tau y. So when the tau is less than tau y, there is a discontinuity in the equation, and therefore this discontinuity is being tackled by introduction of the Bingham model, by regularization of the Bingham model. So now by regularization, an M regularization parameter comes into the picture, and this joint equation turns out to be tau is equal to 1 plus Bn, where Bn is the Bingham number, which represents the ratio of the yield stress by viscous stress, multiplied by 1 minus exponential minus M gamma dot divided by gamma dot. So this is the regularized Bingham model. Usually we could call it Papanastasiou regularization model for the Bingham equation. Now, in order to solve, we need to have the thermophysical properties of the base fluid and the nanofluid, which is usually obtained by doing some measurement, okay, thermorheological measurement. So I'm just representing it. Say the Cp of the base fluid being water is 4179 kilojoule joule per kilogram per Kelvin, whereas for nanoparticle it is 796. Density is around 1000 for base fluid and around 1600 for nanofluids. Thermal conductivity 0.613 watt per meter per Kelvin, whereas for nanoparticles this is 3000. That makes a big difference, because this 3000 viscosity is a significant one. Here you see this is a significant number. This 3000 is a significant number. So whereas the thermal conductivity of the water was only 0.6 watt, it is 3000 for some typical nanoparticle. So how many times it is? It's around 500 times. 5,000 times than the base fluid. So even if we mix very small quantity of nanoparticle, the base fluid, the resultant thermal conductivity of the colloidal solution is expected to be significantly high. The coefficient of expansion is 21 into 10 to the power minus 5 for base fluid, where it is 10 times smaller, just 2.1 into 10 to the power minus 5 for the nanoparticle. Now, because we are mixing the base fluid and the nanoparticle in certain ratio, let us take that ratio as 5. So the thermal physical properties of the mixture, nanofluid density will be equal to 1 minus 5 rho F plus 5 rho S. S stands for nanoparticle solid. F stands for fluid, base fluid. Similarly, we can have this heat, specific heat. We can have the coefficient of thermal expansion beta. We can have the viscosity, and we can have the ratio of the thermal conductivity. Several such correlations has been proposed by researchers and is widely reported in the literature. Though doing the, finding out these thermophysical properties on your own could be an interesting area. It's still open, and a lot of work has been done and going on by different researchers to fine tune, how to fine tune the thermophysical properties, how to find out the thermophysical properties, and how to correlate the thermophysical properties of different base fluid and different nanoparticles. Okay, so these are some of the correlations that are existing in prior in literature, and therefore it has been used. Though an attempt has been made by several researchers in our lab also at NIT Jamshedpur to find out these parameters. Okay, non-dimensional parameters, as I told you, the Rayleigh number. Rayleigh number is defined as Grashof into Prandtl number, where which has been varied from 5 into 10 to the power 3 to 5 into 10 to the power 6 in our case. Bingham number has been varied from 0 to 2 Bingham number, that is equal to tau y by mu f multiplied by Lg beta delta t. This is how we define this, viscous, viscous forces at the denominator and yield stress forces at the top. That is how we come into the picture. This Bingham number comes into the picture. Okay, and the Nusselt number is del theta by del y at the bottom of the surface. Y is equal to 0 multiplied by KNF by KF. So if you do not include this nanofluid into nanoparticle into the fluid, this KNF and KF becomes equal. The Nusselt number turns out to be nothing but del theta by del y. And then we have summarized the Nusselt number by introducing average Nusselt number term, which is nothing but integral of nu over a length dx, where dx is varying from 0 to 1. For this particular investigation, the Rayleigh number has been varied from a range of 5,000 to 5 into 10 to the power 6, that is 5 million. So from 5,000 to 5 million. Bingham number has been varied from 0 to 2. 0 means there is no yield stress phenomena. The fluid is very much behaving like a normal Newtonian fluid. The nanoparticle concentration, volume concentration has been varied from 0 to 5%, and the Prandtl number has been varied from 5 to 100 in order to include wide range of fluids. For example, water will have a Prandtl number of 7, and some hard oils, some drilling muds, drilling oils, dredging oils, they will have Prandtl number of the order of 50 onwards, close to 100. Okay. Boundary conditions, if you take into account the right hand, left hand, top and bottom boundary conditions, has been already discussed. That at the top, there is a cooling, so theta is equal to 0. At bottom, there is heating, so theta is equal to 1. Whereas right hand and left hand walls are thermally inactive, so d theta by dx is equal to 0. How we have obtained the solution? Just prior to my lecture, I was listening some opening statements of Professor Rituraj from JNU, where he was talking about fundamental methods for solving conventional problems like finite element and finite volume, and then there is certain set of problem where these two do not work. Fortunately, in our case, the typical finite volume method works, and that has been employed here. So a finite volume based code with a staggered grid arrangement, and the coupling has been introduced by using simple method. Coupling is required in order to integrate the velocity and pressure fields. To discretize the convective term, second order upwind has been screamed, and to discretize the diffusive terms, CD, that's the central difference scheme, has been employed. For all parameters, the convergence criteria has been taken as 10 to the power minus 6 for scaled residuals. Now, the code has been run for test case of Rayleigh number 10 to the power 5 and Bingham number 0.25 with a particle density of 0.5% and Prandtl number of 10 close to water. Different uniform meshes were used: 40, 40, 80, 80, 160, 160, 200, 200. Those who have been involved in typical computational fluid dynamics and heat transport problem, they must be aware of this technique. Details can be found out in typical literature pertaining to CFD, maybe by Anderson or similar books, or by Chub. Details can be obtained. And finally, this M3 and M4 were found to be quite similar to each other. There was hardly 1% difference in the Nusselt number by solving problems by using these two different meshes, and therefore the M4 was employed to solve the problem. Okay, because being a laminar flow, computational cost was not that much high for this computational simulation. This present study was validated by using reported literature by Ortetani and Turan. Both Ortetani and Turan has significantly reported in literature for non-Newtonian fluids, and similar kind of validation we have carried out for Bingham number also. And another typical parameter selection was pertaining to the regularization, fixing the regularization parameter in the Papanastasiou regularization equation, and we did it for a wide range of m, starting from 10 to the power 3 to 10 to the power 6, and ultimately we settled down for 10 to the power 5, because 10 to the power 4 and 5 hardly there was any difference, and because of divergence at ultra low Bingham number at 10 to the power minus 6, we avoided that one. Okay. One thing is to be taken into consideration here is that the regularization parameters do have significant effect on number of iterations required to obtain the convergence. For example, if I take it as 10 to the power 3, please note that higher the m, better would be the regularization. So at 10 to the power 3, the iteration numbers to obtain the convergence was 5416. For 10 to the power 3, 4, it was 8,000. And for 10 to the 5, it was 10,000. Okay. You see that in the present study, hardly there was any difference on the mean Nusselt number because of the variation of m. So finally, m equal to 1,000 was taken into consideration, and you can see that there was significant, significant agreement between the present result and the result by Turan was there, over a wide range of BN number, except at higher BN, for which we will discuss the reason, at later stage. However, we can say that Papanastasiou model is quite effective, to simulate, to represent this flow, when the BN number is, close to, say, less than 1.5 or so. Okay. Now, let us discuss the results. A lot of computations simulation were carried out, and for a wide range of Rayleigh number and Bingham number and Prandtl number, and then they have been summarized here for sake of convenience. The concise results are being presented. So if we are interested in understanding the effect of Rayleigh number, which represents actually the buoyancy parameters, buoyancy effect, because it's a ratio of buoyancy effect to the buoyancy effect to viscous effect. So Rayleigh number, by varying it from 5 into 10 to the power 3 to 7.5 into 10 to the power 5 is presented here in terms of the stream function and temperature distribution contours. So you can see in figure, where should I start? Okay, let us do it for figure 1.3 first. Bottom part is the heated one. The top part is the cold one. The fluid was primarily, initially stationary, and because of the induction of heat from the bottom, the heat penetrates through the fluid media. It tries to goes up. The heat tries to go up because of the temperature difference. Okay, whereas the colder fluid at the top tries to come down. And henceforth, a convection current was expected to be established in the system. At a significantly higher Rayleigh number of 5 into 10 to the power 5, that is close to 500,000, and a BN of 0.25, Prandtl of 10, with a 1% of nanoparticle present in the system, the bottom part you can see was slightly heated up. The hot region has been represented as dark blue, where the cold region has been represented as light color. Okay, so the dark blue represents the hot region. The bottom wall is significantly covered with the hot fluid, where the top wall is significantly covered with a cold fluid. The reason is quite simple, because of the presence of the thermally active surface at the top and bottom. This behavior is obtained. The hot fluid goes up, and henceforth the hot fluid takes a pattern of C kind of pattern, whereas the cold fluid shows an inverted C kind of pattern. And the core, at the core, where mid-plane in vertical can be seen, it is again, at the top half is dominant by the hot region, where the cold half is dominant by the cold region, bottom half, okay, except the one at the thermally active wall. If you look at the stream function at the set of figures presented in figure 1.4, the right hand of your screen, 4 different stream function plot has been represented for RA varying from 10 to the power 3 at the top to 10 to the power 5 at the bottom, and the difference is quite visible. When the Rayleigh number was small, just say 50,000, 5 into 10 to the power 3, sorry, 5,000, just 5,000, what was happening? There was hardly any movement in the fluid. The fluid, despite being heated up, there were no movement because of the yield stress, because of the heating. The viscous effect that was present there, or the yield effect that was present there, was dominant, and the buoyancy effect due to heating was not sufficient enough to cause the movement of the fluid, to cause the fluid to flow. It was stagnant. Henceforth, the mode of heat transport was purely conduction. Despite it being a fluid, despite it being subjected to a heat gradient, thermal gradient, there was no movement of the fluid, and the dimensionless temperature lines were flat at, you can see at the top. Whereas when it was further increased to 10 to the power 4, the corners, the 4 corners, you can see, they are having a small amount of unmoved material. At the core also, we were having unmoved material, whereas the rest of the fluid, rest of the space is filled with a fluid that is in motion. So what you can see is at the dark here, this portion is unmoved, is behaving like a solid, whereas this white part behaving like a liquid. And henceforth, a solid liquid behavior kind of phenomena is being observed. And once I track down the temperature distribution, you see a flattened approach at the corners, 4 corners, flattened approach because of presence of the solid particles. Whereas it is varying significantly, non-linear behavior in the temperature pattern is being shown in this part, whereas this part again, it is slightly linear, okay? And this variation comes because of the movement. This non-linearity in the temperature pattern comes into picture because of the heating. Once it is increased to 10 to the power 5, the amount of unmoved part of the fluid reduces, which further reduces when it is increased to 10 to the power 5. From 1 into 10 to the power 5 to 5 into 10 to the power 5, it further reduces. The non-linearity is further strengthened. That shows that the convection current has gained a lot of significance, significant strength. And that's why this curves is very, very, very non-linear in nature. Okay, I hope this figure is self-explanatory, and you'd have got some information. If I summarize, then I can say that the Rayleigh number has an effect. If the Rayleigh number is low, the yield stress overcome the behavior and yield stress is dominant. There is no movement. If the Rayleigh number is high, the buoyancy effect overcomes the yield stress, and henceforth there is movement. So it's a game, it's a fight between yield stress and the viscous stress, this buoyancy stress, which goes on. If the buoyancy stress dominates, there is movement in the system. If the yield stress dominates, there is stagnation in the system. Okay. Similarly, the variation of dimensionless temperature across the Y vertical midline has been shown. So close to thermally, this is thermally active wall. X is, Y is equal to 0 and Y is equal to 1 is thermally active wall, and in between you are having the fluid. So the close to wall, you had a linear temperature distribution. Here also you had linear temperature distribution. In the middle also you have linear temperature distribution. So close to thermally active walls and core, you had a small solid core kind of thing. So linear thermal distribution, and this linearity is lost once the motion is instigated in the fluid and the fluid moves. Okay, so this is how the theta varies. You can see here for 5 into 10 to the power 3, there was no movement. So it was perfectly linear, something like representing the conduction mode of heat transport, where theta is equal to, theta is represented by nothing but a linear with respect to y. So you can see that Q is equal to minus K d theta by dx. Conduction mode of heat transport, the Fourier's law of conduction, is represented here, and the line is perfectly linear. Whereas as you increase the Rayleigh number, the discontinuity comes into the picture. The non-linearity gets strengthened as you increase the array. In fact, for array of 7.5 into 10 to the power 5, it is significantly non-linear, except at here, and slightly in the middle. It is perfectly non-linear. Yeah, this one. Okay, this is how, my dear friend, this non-linearity has been represented. The same is graphically represented in figure 1.7, where hot and cold fluids are represented in red and blue color. I must tell you that this was published in the journal of this material has been published in I think in Journal of Heat Transport, and then Indian Journal of Chemical Engineering, and Journal of Non-Newtonian Fluid Mechanics. In 3 SCI journals, these results has been represented. I have come to showcase the effect of Bingham number. You can see lower the Bingham number at the top of the figure 1.9, the shaded part, the dark color part, which is representing the unyielded region, is small. If you increase the Bingham number, the unyielded part increases. And then you come to a situation when Bn is equal to 1.75 at Ra is equal to 10 to the power 5. It's not 105, it is 10 to the power 5. The fluid ceases to move. The fluid is perfectly stagnant. There is no movement. This Bingham number is called critical Bingham number, at which there will be no motion, at which the fluid will behave as a solid. So in fact, in non-Newtonian parlance, non-Newtonian paradigm, we do not differentiate between solid and liquid. Rather than we consider it as a material, and we try to find out the substance, different components simultaneously. Same substance may behave as a solid and sometimes as a liquid. You can see here. The core is behaving in case of 1.5. The core is behaving as a solid, whereas there's a fluid. Okay. In case of Bn 1.0, there are two non-moved part. Rest of the fluid is moving. Okay. So the Bn number is having, the Bingham number is having significant effect on this phenomena. Same we have studied for what you call particle concentration, for different concentration, starting from no nanoparticle to 5%. And there also we have found out that the velocity contours and the temperature distribution, the stream function distribution, they are also affected. The extent of non-linearity, the extent of strength of the convection reduces once we increase the solid mixing of nanoparticle in the fluid is concerned. Okay. Here, finally, for this particle problem, two things has been represented. The effect of concentration. You can see the effect of concentration. Okay. For no nanoparticle and for nanoparticle, two figures have been plotted in order to understand the effect of nanoparticle. You can see that these are thermal distributions, red and blue. Red represents the hot fluid and blue represents the cold fluid. Hot and cold we are describing in respect to the heating conditions. You can see that with the introduction of nanoparticles, the strength of stream functions are increasing. For the same location, it was 1, 10, 19, where it was 2, 13, and 24 when the nanoparticle is present. That shows that the inclusion of the nanoparticle significantly enhances the thermal transport capacity of the substance, thermal transport capacity of the system. Okay. And that is why these stream functions are being strengthened. That is why the extent of colder region reduces when we ultimately, because for each case we have been deriving the Nusselt number, which ultimately helps us in calculating the total behavior. And for all these cases, for all the range of Rayleigh number varying from 10 to the power 4 to 10 to the power 6, Bn from 0.25 to 1.5, and particle concentration from 0.05% to 5%, and for a fluid ranging from PR 5 to 100, Nusselt correlation were calculated and proposed, and it comes out to be something like this, where the average Nusselt number was found to be equal to 3.155 relay to the power 0.278, Bn to the power minus 0.233, and multiplied by 0.044 plus concentration to the power 1.338 multiplied by PR by 2 minus 0.010 PR to the power minus 0.096. So Nusselt number, average Nusselt number was positively depending on RA. RA increase indicates that Nusselt number will increase. Bn increase, that shows negative effect. So Bn increase hoga to Nusselt number will go down. Same with phi. If phi goes up, then the Nusselt number will also come down. This simplified correlation can be used by engineers to to calculate the effect of all these parameters RA, Bn, phi, and PR. So a single correlation has been proposed. I think I'm done with my presentation, and I'm open for your, what you call your queries, your questions pertaining to this. And if I summarize, then I can say that Rayleigh number, Brigham number, particle concentration, and Prandtl number are having significantly effect on thermal and fluid transport behavior. Mean Nusselt number is enhanced when the RA and phi increases, where it falls when Bn and PR increases. Okay. The presence of nanoparticles significantly enhances the heat transport phenomena, and ultimately a simplified correlations has been present. I'm open for questions, please.
Thank you, sir, for your insightful presentation. Now the house is open for discussion. If anyone is having any queries, they can unmute themselves first, and they can start asking their queries. Any questions from the audience side? I think no one is having any questions. So once again, thank you, sir, for giving your valuable time in this lecture series. Now you can unshare your screen, sir.
Thank you so much.
Yes. So now we will try to adjust Rituraj sir lecture in any of the upcoming days. So now I announce the end of the today's lecture series, and tomorrow again we will start at the same time from 3 p.m. onwards. And tomorrow we will have 3 lecture series. We'll have 3 experts. First is Dr. Manish Kumar. He will deliver his talk. He's from NIT. He is an assistant professor in NIT Jamshedpur, and his title of talk will be Adaptation of Immerse Boundary Method for Solving Large-Scale computations of Complex Industrial Flows. And the second expert will be Dr. L. Harish. He is from